All right, wait, what happened? 5? Or 4?
Yeah.
5? 5 is what?
Wait, but that is for number 1. F2 is first order as it shows in the equation, right? So F, so the third one has to be wrong too. If one is wrong because it says it's first order and 3.
It is first order. NO2 is not second order because look, where's the coefficient right there? No, 3 doesn't have to be wrong. They are both first order. It's a slow step, right? So they both coefficients is 1. So that means rate is equal to K NO2
Oh, it's wrong on the
and then F2. Yes, NO is wrong. So it's first order, both are wrong.
I just thought the F2 came.
Okay. Now we said F is an intermediate. Is it correct? Yeah, we make it, we use it. So is that intermediate? That's correct. First order, that's also correct. This is wrong. Okay, got it? Y is D. Okay, look at number 6 then. 6, what do we get? You should get C. Because we're looking for excepts, that mean things that are not true, because we said each are true except. Okay, let's talk about heterogeneous. Heterogeneous means difference. That's what you have to know. Difference. Remember, we talk about heterogeneous mixtures, like salads is a heterogeneous mixture because you can see different pieces, right? The tomato, lettuce, whatever. But when you say sugar water is homogeneous because you can't see sugar and water separately. They're together. Okay. Also, let's talk about each one. You should see that A, B, D, and E are true because take a look. Catalase change the rate of chemical change. True or false? True, right? Because they make it faster. Catalase make them faster. Catalase and do not undergo permanent change. True, because they are used and then remake again. Okay. They presence lower the activation energy. That is also true. Remember when we draw in the graph, catalase versus uncatalyzed, right? Catalyzed one go down. Okay. Present that show the change, the decrease of potential energy or activated complex. Remember, activated complex is that transition state that happened at the top of that graph. So here is where we have activation complex or the transition step. And then from the reactant to the top of the hill, that is my activation energy. So this will go down if you have a catalase reaction. So that means if I have reaction that is catalyzed, you will have something like that where this is go down, right? So this is catalyzed. And then this is uncatalyzed. Okay. Make sense? Okay, let's look at 7. 7, where do we get? You have a question about this? What happened? For the 6, what happened? 6E? C. Yeah, 6 is C. Why? Because A, B, D, and E are the true statement. And only C is a false statement because heterogeneous mean different. So that means catalase is in a different phase than the reacting particle, the reactant. Okay? So the reactant could be like solid and the catalase could be gas. Reactant could be like liquid and the catalase could be solids. Okay? All right, let's talk about 7. What do we got for 7? 8. That's the easiest one. Okay. You can't do 7. I will question what you've been doing. All right, 8. A?
Yeah.
Quantum rate law reaction, increase in concentration of H iron, where affect. Okay. It doesn't matter. Take a look at your rate law. H is not part of them. Do you see that? It's E. It doesn't change. Make sense? All right, number 9. Number 9, no, not D. B.
Oh, that was the one I wasn't sure about.
Okay, so according to the rate law for the reaction, decrease in the concentration of iodine iron will have what effect? Take a look. What is the iodine iron? Iodine iron is this guy, I minus 1. So what happens when this decreases? The rate also decreases. Right?
Because the reactant, wait, no, what?
It's part of the rate. So if this decrease, this also decrease. So if this decrease by 2 times, this gonna decrease by
I thought you said that was like
2 times.
something about the rate.
In here, if I have a rate equation, why is it not true?
Oh,
First order. So if this go down by 2, this go down by 2. First order,
right.
right? Okay. Question? About 9? 10?
I hate this.
D. Yes, it is D. Okay. So what's happening?
Wait.
All the following apply to the reaction above as carried out in a constant temperature in a sealed rigid container. Okay, same T, same V. What happening? Well, take a look. You have all the gases. Okay, so you have 2 mole of gas, right? Here, 1 mole, 2 mole of gas. Here is only 1 mole. So total pressure decreased, true?
Yes.
Yes, it should be. You have less particle, right? So remember, less mole, less pressure, right? Especially because we're keeping T and V the same. Okay, the rate of reaction is decreasing. True, because as you let it go, as time go, they're gonna decrease the rate of reaction. That's true. Entropy is decreasing. True, because 2 versus 1, less particles, less entropy, right? Entropy is delta S. Changing entropy, delta S, less particles. Okay, frequency of collision between A and B molecule is gonna decrease. That's true too. As the reaction go, there's gonna be less of them, less collision between the thing. Okay. So only thing makes sense is D, and also D is definitely false because as this reaction go, I'm gonna have less C. No, I'm gonna have more because it's a product, right?
Unless you're playing it backwards.
Yeah, unless this is a reversible, then yeah, we can talk about it differently, right? Okay, let's talk about 11. Okay, so we want to say formation of XY. Okay, this is the one that you have to remember how to write the rate equation. So rate is equal to, right, let's write these two. This is a reactant, so it's mean negative concentration of Y over delta T. Remember that this is 2, okay? It's gonna be equal to the product, so just mean concentration of XY over delta T. Okay, notice that you are given this already in here, so you just plug in that in. So that number divided by 2 and change negative to positive. So the answer is D. Right, the rest is math. I'm not gonna do a math for you guys. Okay, let's look at 12. Another one IB 1, 2, 3. That is C. Question about C? Phương. Alright, so why it is C? Let's see. So consider hypothetical reaction here. Okay, reaction started by placing A and B in a syringe. Okay, no chemical equilibrium is established. Okay, so which change caused the immediate increase in the partial pressure of B? So increase in the partial pressure mean what?
I mean, it's the only that.
More B is in there, right? More B gonna be in there, so that's why more partial pressure. Okay, so based off of this, if you're looking at this, adding of B, yeah, will definitely make more pressure, partial pressure of B, because you have more B, right? Now, 2 said decreasing the volume of the vessel. That will also do more pressure because pressure has to do with volume, right? Less volume, more pressure. Make sense? Okay, adding on AB is not gonna do it. In fact, if this actually exists, right, it might go to this. If this is like a equilibrium equation, then it might work because if you add this, it's gonna make more of this, and therefore it will increase. But this is not equilibrium. This is just one line. Therefore, adding product will do nothing to the B. Okay. 13
A.
is E.
What?
Let's talk about it. Okay. Y is E. Okay. So we said for the two first order reaction, different in substance, we got this. Okay. So this means, well, let's try to figure out why is this. You think it's A. Let me see why it's not A. Doubling the concentration of A will have half effect on half. Okay. Do you guys know that this was first order? First order? Okay. Both are first order. That means concentration will have effect on half-life? No, it won't. A is wrong. Make sense? Concentration and half-life had nothing to do with each other on the first order reaction. Okay? Now 0 and the second, yeah, they do. But first order, no, they don't. Okay? B, certain number of A will react twice as fast as certain numbers of gram of X. Okay, notice the questions at grams and not mole.
Wait, does that mean it's automatic?
It is wrong because you can't compare grams, can I?
No.
Because I can tell you I have 20 gram of calcium and then 40 gram of hydrogen. Does it mean there is twice as many hydrogen as calcium? No, it's not. In fact, a lot more than that. Right? Make sense? Molar mass. I don't know anything about molar mass. I cannot just compare gram. Can't compare grams, guys. Okay. C said the number gram of X will, again, same idea. Numbers gram is an issue. Okay. Now, if they give you mole, that's a different answer. They give you grams, not it. Okay. Rate of constant of AB is lower than rate of constants of XY. Wrong. It should be higher, right? Because look at the half-life. Faster half-life, meaning that reaction is going faster, right? Shorter half-life, faster. It's gone way faster. This is not lower. This is actually higher. Got it?
Yeah.
So that end up with E. E is the right one because remember, it's comparing mole. 3 more A will react faster, more rapidly than 3 more X. That is the correct one that we're looking for. Got it? Question? Okay. See? Again, I said read. Yes? Read the question. Okay. The next 6 equations, use that one. Number 14, what do we get? E. Okay? Self-explanatory, very explanatory. You just plug it in, solve for it. Yeah? Okay. Let's talk about number 15 then. See? Again, that also fairly explanatory, yes? Because 3 concentration, third order, so to speak. That is third order unit, right? 4K, yes? All right, 16.
E. E. No? I don't know. Can you explain?
No. All right, let's go through that. Okay, here's C.
Yeah. What the?
So, okay, concentration B is decreased to 0.4 molarity. So what is it saying is it start with 0.1, right? B start with 1.0 molarity. Now it's 0.4 molarity. So that means B go down by 0.6. 0.6 is gone. So if you go back and look at the top one, B and C is coefficients of 1, right? So that means C is going to go from 0 to 0.6 molarity, right? And then if you look at A concentration is go by 2, right? So if you look at A, I have no room. A start from 4 mole, okay? It's going to lose 0.6 times 2, so it's going to be losing 1.2. So therefore, wait, is it 1.2? Yeah, 2.8, right? Yeah. This is 1.2, right? Okay, let me rewrite it down here. Let me rewrite it down here for this question. So you have 2A plus B go to C, right? Okay, concentration A start out with 4 mole. Concentration B start with 1 mole. Now, if you guys don't know where this number from, it's up here, right there. You see that? Beginning try times 0. Okay, so in the number 16, it said you're gonna to decrease 2.4. So that means it's gonna to go to 0.4 molar. This is how much it's gonna be left. So that means between here, the change is 0.6. Right? So this is started with, this is initial, this is change, and then this is the ending. Right? So notice that I need 2A for 1B. So if it changed by 0.6, how much it should change in here for A? 1.2. It's lose it twice. Okay? So that means 4 minus 1.2, you're going to get 2.8. Okay? Make sense? And then on the C, you can do the same thing. It starts from 0. We're going to say point plus 0.6. So that would be a 0.6 at the end.
Wait, but that's if you subtract from B, why are you because C is the
Okay, make sense? This question didn't ask for C, but I'm also showing with it. Yeah. Okay, guys, I know that last night is really rough, but let's pay attention. 17, what's 17?
DD.
Correct? Okay.
Yeah.
Rate decrease because the concentration reactant decrease. That's only makes sense. Especially if you look at this, second order and first order. Yeah, definitely they both affect the rate. Okay. Let's look at 18.
A.
Oh, not good. All right.
A.
Let's look at it. Which apply to this reaction if it proceed at the constant temperature? Okay. Constant temperature mean what? Okay, first of all, constant temperature, that's gonna mean K is constant. Okay, now let's go through each one. As if reaction proceeds, you're right, the rate of reaction will decrease. Why? We're losing reactant because less reactant. Right? Less reactant, less rate. That makes sense. Number 2 said collision between reactant molecule remain the same, effectively remain the same.
No, because it increases.
Explain.
Fewer collisions, but the collision has the same effectiveness.
Yeah, fewer collision, but the collision effectiveness is still the same because see, if these two hitting each other, they still hit each other with the same amount of energy because the temperature is the same. The speed of the collision is not changing, but yes, there is a fewer collision. Okay, so less reactant meaning fewer collision. That is true, but the number, this one is not talking about number of collision. This is saying affected number of collision between reactant molecule. So that means when they hitting each other, we're talking about assuming that they still hit each other. What is the effectiveness of this when they hit each other? Yeah, I mean, it still should be about the same because same temperature, same amount of speed that they are running into each other, right?
Wow.
So this is true because same T, same KE, right? Same amount that they are running into each other, same speed of running into each other. Okay, so they have the same energy. Make sense? Less collision, but same energy collision. All right, frequency of collision between reactant molecule the same. That's the boo-boo. We just said it.
Not the big no. That's why reaction speed is low.
Right? So therefore the answer is C. We got it. All right, let's talk about 19. What do we got? Uh-oh. 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 Let's look at them. Okay. So when a temperature increase at a constant volume.
It's not E.
Well, first of all, temperature increase.
K is not the same.
K is not the same. 2 is already wrong. Okay, so that eliminates your D and E. See that? Okay. And B is also wrong, yeah. So then you get 1 and 2. I mean 1 and 3. So if you can prove 3 is right, you're done. I don't even need to look at 1. 1 is automatically true.
Oh,
right?
It's C.
So let's look at 3. Is 3 true?
Yeah.
Yeah.
Oh, okay.
Okay. T increase, bigger K. Bigger K mean
Faster.
bigger rate, faster rate. Yes, faster.
Temperature increase, reaction rate increase.
Yeah.
So basically those affect the
Yeah. That's it. Okay. And remember, like one of them, I said increase the concentration. That's the reactant, and then only some reactant technically do increase the concentration on the rate law, right? Yeah, depend on order too. All right, let's look at 20. Koi. Koi. And then you look around. I mean, your name is Koi, yes? All right, what do you get for 20? A?
A.
Yeah? Yeah. Yep. What is that? Okay.
Wait,
A is the first letter
I'm
of
a
the
little
English
bit
alphabet.
confused on
Right.
2.
Open alphabet.
I'm a little bit. Wait, no. For 2, I'm guessing it's because some reaction only have 1 step.
This one?
Yeah, for 2, it's wrong because some reaction can have 1 step.
Yes. Some reaction can have more steps. So not just unimodular, they can also be bimodular.
And
Right.
3 is wrong.
Yeah.
Yeah, alphabet, definitely.
Okay. Any reaction. So yes. Reaction mechanism is just talking about like those steps. So like this, those are reaction mechanisms. Step 1, step 2, step 3. And then when you add it together, you get overall. Right? Okay. All right, let's look at 21. Huh? Go down? Yeah, 20 is A. Why is 3 wrong?
Because they can include it.
Yeah, because any steps, they do have intermediate in the steps. Not overall, any steps. So, remember this one? F is an intermediate. It was part of the steps. You guys see that? Yeah? So, any steps. The keyword is right here. Any reaction mechanism. That means any steps. What talking about. Okay? All right, 21. What do we got? Yes. You see why it's A, right? Yeah, it's like 4 half-life. Cut. Right.
It took forever.
That's a outlaw.
That's in 90
So they're never gonna.
Yeah, right there. It's 90. Okay, 22.
C.
Okay. Do we have an issue? Easy, right? 1, 2, 3, 4. Add them up. All right. 23.
Yeah. E.
Uh-oh.
Somehow it always seems wrong.
Uh-oh. Somehow, like, you guys do not like the 1, 2, 3 question.
Yeah.
Uh,
23.
yeah, 23.
It's C.
Easy.
Hey! First
All right. All right, let him celebrate. All right, let's go over why the rest is wrong. Okay, let's take a look. Which statements must be true about this first step in the reaction mechanisms?
When I see it coefficient, I just automatically think it's wrong.
Okay, it's not automatically wrong, but it is wrong because it's that coefficient of the rate must correspond to the exponent on those same term in the overall rate law.
Yeah,
Okay.
No.
No, because did we know if
That's
this
the order.
fast or slow? Did they tell you?
It's including the slow stuff.
Yeah, they said has a 3-step including a slow step. The first step is this. But do we know this step is slow or fast?
Wait, can you tell me what happens if the first is faster step?
If this one is a fast step, then it's not it. Now, people that think that one is true is because you are thinking that this is slow. If this is a slow one, then this is a true statement. But you don't know. The question is, I don't know. They didn't say this is a fast step or a slow step. They said there's a 3-step. One of them is slow. See that? Yeah. Only slow step will be equal to the overall. Now, also, if that slow step happened later on, it's not it because you have to check for intermediate to cancel out. So the coefficients won't match anyway in that case either. Okay. Number 2 said no further step can include intermediate. Yeah, not true. Since we make it, we got to delete it back somewhere. Yes? And yes, since you're gonna have B2O3 minus as a reactant, you should, because take a look. B2O3 is part of my overall reaction. It should be reactant somewhere further along the line. Yes? All right. 24.
D.
Good.
Yes.
Okay. Got it? Because increasing more H, that means there will be more collision between the reactant. Yeah.
That's an
All right. 25.
D. B. B. B.
Uh-oh.
B.
E.
Wait, what? Wait.
Oh, that increases the concentration.
Addition of
Oh, just water.
okay. Shh. Yes, you guys heard it. What Kevin said. The water acting do decrease the rate because take a look at what is your reactant. They are aqueous. That means they dissolve in water. That means the more water you have, the less concentrated you are. Right? So the water mess with the concentration. So this lower
Wait, what about
concentration.
What about the OH?
Yeah.
I'm going to
I
explain
get
that one.
Doesn't react to the H plus?
Wait, what? Oh.
Yes, you're right. The adding of OH, because remember, OH is what?
Oh,
It's a base. Base is gonna neutralize this H plus. So adding of this is gonna remove H plus. These two are pretty much the same thing.
oh, not only that, but it'll create more H2O.
Yeah. And also, so you're gonna lower the concentration of aqueous reactant, right? Make sense? So therefore it's E. Yes, 25 is really tricky. Got it? Okay, 26.
A.
Uh-oh. We got A and a C. What do we get? Any more vote?
Yeah, Kevin's right. I'm pretty.
Yes.
I don't know.
Yes, it is A.
Wait, I said A. What? Oh.
All right. So let's go with this. What is the effect of adding B2 liquid to the systems? Okay. Assume that negligible volume change. Okay. So adding the B2, what's gonna change? Well, take a look at the system. This is only one direction. So adding the products, does it gonna change my stuff? Probably not.
No.
So therefore, it probably won't change the mass of the reaction, and yeah, it's not gonna change the oxidation reduction stuff of it. Also, oxidation reduction is wrong on that one. Okay, take a look. That one you have to double check this one. I don't know if you guys noticed, this is a redox question, the oxidation reduction also. Because see, we already did it a long time ago. Remember the oxidation number? So this is 0. This is -1. This one I have to double check because this is -2 times 3. So that means -6. -6 -1. So that means this has to be +5. So take a look at BR. BR go from -1 to 0. So what's happening?
What's happening?
is gaining electron, right? I mean, no, not gaining, losing,
Oh my God.
because -1, so it's losing. So it's Leo. So that means is oxidation. And then when you're going from here to here, you're going GER, so reduction. Right? Do you see that? Okay. So actually, hey, they do have a correct oxidation reduction. I thought that was wrong. All right, so they do have the right oxidation reduction in here. Right. Because of this thing, this last sentence. I don't know if you guys noticed that one. Assuming negligible change in volume. So we're not changing the volume, we're not changing the mole, we're keeping their concentration still the same. My rate will not change. Yeah, unlike previously where you're adding water, so you're changing the volume of it, which means I'm diluting it, so my concentration lower, therefore my rate decrease. Here, yes, I'm adding Br to liquid, so I'm thinking that it might change it thing because more volume, but here they said the volume is changing negligible, so we're saying that concentration doesn't really change, right? Meaning that my concentration reactant is not affected by it, so therefore it will neither go up or go down, right? It will not change because concentration of reactants is not change. Make sense?
Yes.
Kevin doesn't feel happy about this.
No.
All right. Okay. Damn firecracker. All right. Right.
Oh, I'm just spacing
I know. I can kind of tell. You guys are like,
Is it B or A?
B or A. You can't say B or A.
B or A? Yeah, D.
Uh-oh.
What?
No, it's B.
B.
What?
It's B. B. It's B. B.
B.
The
B.
thing is C
L.
also
A.
works.
B.
L.
All right. Let's go through this.
I'm good. That's okay.
You guys just literally said every single possible number. All right. So, I mean, one of you guys are right. I don't know which one. Let's go through it. So, value of change in enthalpy, delta H, and activation energy for the given reaction are known. The value of EA for the reverse equal to. Let's try drawing this.
Oh my gosh. It's reverse again. I hate it.
Okay. Okay, you have this. I'm drawing endo just so that we have this. Okay, this is my delta H, agree?
Yeah.
For the forward reaction. And then this is my EA,
Wait, your exothermic one.
right? I mean, did they say exo?
No, wait, did it?
They did it, right?
For a given reaction.
A given reaction. So we have that. Now take a look. That's forward. Okay, that is forward. I'm gonna use pen to do the reverse. So reverse. This is my reactant, and then this is my product. Agree? So now this is an exothermic reaction now. So let's see what is my things is gonna be. This is my delta H. Agree? Yeah? From product to reactant, except it's exo, so it's gonna be negative. So this is gonna be negative. And then my EA is right here. Okay, so we got it? Pictures? All right, let's go through and find out.
Oh, I
So
remember this.
okay, so EA for the reverse is gonna be equal to, okay, so reverse for EA, this pink one is gonna equal to this big one.
EA minus delta H for the
EA.
Ah.
So therefore the answer is C.
Hey.
Ah.
Got it?
Exothermic.
Oh, you can draw the exothermic one, it should still be the same. So yeah, because you just draw forward and backward. Let's try. Let's try.
Again.
Okay, exothermic one, right? Okay. So yeah. This is EA. And then this is my delta H. Yeah? Okay, let's draw the reverse. So the reverse This is my EA. This is my delta H, except this is positive. Right here is a negative delta H. Same idea. So the reverse EA, which is that pink EA, will be equal to the sum of EA plus negative of that. Because negative, negative make it positive. Yeah. Make sense? Because it's still gonna be the same. Either way, whichever one you draw. Yeah? Question? Alright guys, don't go blank out here on me. Yeah? We got it? Yeah, 2 graph. Okay, how about 28? What do you guys get? E, yeah. Okay. Yeah, adding catalase will decrease the potential energy of activated complex, which means you decrease that EA. All right, 29. Oh no, another 1, 2, 3. Let's see. Maybe this time we'll get it good.
Oh my god.
No.
Again?
Okay. Yes, 2 is the right one, but not 1. It should be B. Let's take a look at it. So the rate constant for gas phase reaction can be increased by doing the following. So gas reaction. How do we increase the rate? Okay. Now you said that increase the concentration of reactant.
Wait, no, it's a gas.
Is a gas. In a gas, increasing the concentration of reactants. Yeah, well, if I change in my volume, you will still have an issue with that one. Okay, so just increasing the concentration doesn't quite work that well because they are gas and also they occupy. So pretty much you are better off saying the moles increase rather than the other one. What is this? Temperatures. Yeah, decreasing the size of the container. Right? Yeah, no. Okay. Okay, so changing the temperature will change the rate constant. Okay, changing the concentration and size will change the rate, but not the rate constant. Yeah?
Wait, increase.
Okay, I think I didn't explain it quite well. Yeah, it's a gas, but that's not the keyword. The keyword in there was what?
The rate constant.
Which means we're looking for
K. So
K.
it doesn't matter if the concentration.
yeah, K is not changed by concentration. Concentration will change the
Oh, only temperature changes.
yeah. This
Oh, okay.
changed the rate. This also changed the rate.
Wait, what did you?
Only this changed the rate constants.
What did you get for 28?
E
E?
is a definition. Yeah. Make sense? Do we got it? 29? E. Is that, I don't know. 30? You gonna get 30? B.
Oh.
Okay? Yeah, catalase make it alternating pathway, just kind of like lower the activation energy. 31? Yes. Yes. 31 is E. Yes.
30 is E? Oh, okay.
32?
D. E.
Mm-hmm. D.
E.
D. Yeah. Alright, I know. Okay. So you guys see what it is? Yes? Yes. Okay, because you just look at coefficients. Alright, 33. Ooh, that should be good. What do we get? Actually, I showed you this graph before. This is the Maxwell-Bowman graph that you're looking at. You guys remember Maxwell-Bowman graph? The bell-shaped curve? D. Yeah, the bell-shaped curve. Remember, the temperature, the more temperature, this graph shifts this way, okay? Because you have more gas molecule at the higher energy. Yes? Make sense? Maxwell-Boltzmann curve, okay? So that's the relationship between temperature and a kinetic energy pictures, okay? Yeah? Yeah, that's a phase. This is Maxwell-Boltzmann. Oh, a lot of graph. All right, these two, everybody should get 34 and 35 correct. What do we get? B and B. Easy, right? It's the same question and same picture too. Yeah, same question, same picture. Yeah, yeah, yeah. Okay, just write it a little bit differently so that we can see the difference. All right, okay, so we're now matching. 36, 37, 38, 39. Let's match it up. Okay, 36 at the rate law for which unit of the rate are equal to unit of the rate constant. Yes. Yes, I'm just gonna write it next to here. 37? E. Okay, 38? What? B. And 39? D. All right, let's go over 38 because I heard. All right, so 38 said rate law for the represent the reaction which doubling the A and doubling the B keep all the same will lead to fourfold increase in the rate. Okay, notice that I double both of them fourth time. So that means I double each one the rate double. Or either that or one of them doesn't matter and one of them was second order. So I'm looking at overall second order for B. I mean for the 38, right? So 38, either I'm looking for, see, because what they said is I double A, double B, and then 4 times the rate. So either A is first order and B is first order, or A is second order and B is zeros, or A is zeros and B is seconds. Make sense? It's one of those. Got it? And the only one it makes sense in this case is B. Right there. A is a second, B is a zero. Okay? Make sense? Because that's the only one they are giving. Got it? Question? Right? So make sense that this one has 3 different answers possible, but based off of here, that's the only one. All right, let's go through some definition. Notice that the next 3 probably not asked by AP like this, or actually these 5, 7 questions. But anyway, so these are kind of a more definition basic questions. So let's go through. 40 is A. Okay, 41 B, and then 42 C. Yeah, A, B, C. All right. Okay. All right, 43. Another C. Okay, we got it? Okay, the rate of the reaction will increase, but K will remain unchanged. Well, let's see why. Okay, make sense? All right, 44. E. Okay. Make sense? Because what do we use? We use the coefficients right here. 1, 2. So every time I made 2 of the NH3, how much N2 I'm losing? 1. Right. So that means half of the original, right? So if I make 1, I'm gonna lose half. If I make 2, I'm gonna lose 1. If I make 4, I'm gonna lose 2. So pretty much half of this one increasing rate. Make sense? Okay, 45 is D. Oh. All right, what's happening? So the first order with respect to D and the second order with respect to E, which are the following, will result in no change in overall rate. Okay, decreasing D by a factor of 4 while you're halving the E. Okay, so take a look. we said D is a second order. I mean, D's first, sorry. E is a second order, right? So take a look at the question. Which one doesn't change? Increase D by 4. So let's just say 4. D is 4 here. 4 to the 1. We're good. Okay, E is half. So that means that's going to be half. Take a look. What do you get?
Oh.
That's 1. Nothing changes. See that? I mean, if you want, you can say 4 eggs and half eggs. But yes, do you see that? Yeah, nothing changes. Okay, 46 is A. Yeah, we got it. Chemical reaction increase. Except for if you activation energy is higher, that's the one that's gonna go down, right? Activation energy is what make the reaction go slow. All right, 47. You skipped it. All right, let's go over that one. Oh, do you see that Maxwell-Boltzmann curve? Let's see. Because you're heating or you're cooling down, the number of gas molecules should not change. Yes? Assuming that nothing is escaping. Yeah, that's what I'm saying. Assuming that nothing is escaping, right? So total area is the same since the number of molecule doesn't change as a result of heating or cooling. So this area here is the same thing as this area underneath that dotted one. Make sense? Okay. $48. Oh, let's go another one for another one. Yay! I don't know how to say this one. It's D. We all get D? Yeah, you're right. Yes. So notice that we talk about the first one to be true. Rate law must be determined experimentally, cannot be told for chemical equation. Okay? Boy, step by steps is actually done by the experimentally. That's how they figure out step by step. So those are not chemical equation alone. Okay? Zero order have a rate constant equal to rate. Yes, it is constant. K is equal to rate. Okay, straight line graph can be obtained from first order by plotting the reciprocal. Okay, that is not it. Reciprocal is which one? Yeah, that is wrong. That should be second. Okay, either though you can say ln. Yeah. All right, 49. B. Yes. Again, I'm not going over it. That's just unit. Yes. 50. Yes. Another one right. Okay. So, yes. Notice that reaction is definitely third order overall. 2-1, that's 3. Okay, the unit is definitely off. That's not it. It should be per m's, yeah, negative, not positive. Right? So let's see. And then it's not doubling Y, right? It will affect it because it's a first order. Okay. Right. Okay, 51. B. Good. Got it? 4 order overall, 2, that's 4. Doubling both while keeping the temperature the same. That's gonna be 16 times because 2 squared, that's a 4 times 4, that is 16. Okay? 52. E. Good. Same idea again. You are doubling and tripling. So x is double, so that's a 2 squared. Y is triple, so just 3. So 2 squared times 3, that's a 4 times 3, that is 12 times the rate. Everyone see how it's got it? Basic math. Okay, 53, sorry. Skip all of them. Okay. Ooh, that's a hard one. That's a slow and fast one. Notice your slow is in the middle, followed by your fast, and then you have an intermediate. You got to delete this intermediate. Let's go through that one. So, So how we gonna do it? So that's gonna be K time F time A, right? Make sense? From the step 2, that's what we get. Okay. Step 1 is a little bit complicated. Step 1, I'm gonna do 2 different ones. I'm gonna do the reverse in pink, and then I want to do the other one in black. Okay, so I'm gonna do reverse in pink, so that we have 2 equations that you can see. So the forward direction is gonna be K time A time B. Yeah. If you want, you can say K1. Okay. Reverse reaction, you're gonna say K inverse time F. These 2 are equal to each other. Okay, these 2 are pretty much equal to each other. So then, F is basically replaced by AB. See that? See that? So then we're gonna say K time A time B time A. Another word for saying is K time A square B.
But why did you tell me? Why did you tell me 2A?
This is original A. I just show off F as an AB,
Oh,
right?
and then you replace the A. Oh.
So it's
Right? This is replaced. So 53 is? It doesn't occur with the reaction. Because remember, the only reason why we have to use a first step is because I have that F. I have to get rid of that. Because it's an intermediate.
Right.
So let's say, here, you just say A and B here, and then this is not there. You don't have to do that intermediate stuff. You don't have to replace it like that. Yeah, no. Step previously to replace it. Okay, 54. Alright, that's easy. You should always be able to do overall. Ooh, that's easy. Also, 55. What order is this? Yep, second order straight line plot. Yeah? Sarcasm on that one. Alright. 56. A. Again, first order is ln, slope is negative k. Okay, that's from that table that I should show you guys earlier. Okay, that one sheet where all 0 for a second is on there. Use that one. Okay, 57.
Wait, 56.
You got E? Yeah?
Wait, what?
It is E. Alright, so I guess
Shoot, I misread it.
you misread it? Okay, good.
I thought I said dependent.
Yes, it's independent, which is true. OH is not, right?
Wait.
Okay, got it? Because if the step 1 is slow, right, as they set it here, we can say that rate is basically equal to K time Rx. That's it. And it's first order. Okay? All right, number 58. 8. Good. Hey, she's on the roll now. Sometimes it helps
Wow, I was
to see everything, right? Okay, so you see, right, it was 1. Okay. Yeah. Let's go to the other one. 59?
E.
E? Yep. Okay. Catalyze preset at the end and change because you made them back. Ooh, this one, you guys figure out the rate law? Yes. We all got E? X, Y? Yeah, W doesn't matter, right? Okay. Anyone want me to do 60 or we got it? Yeah, we got it? Nothing mean yes? We got it? Okay. Guys, you guys had to speak up. Alright, 61. 61 is easy. Once you get 60, 61 is easy. You just plug it in, solve for it. Alright. Wait, actually, not plug in software. You just do the what is it called? Rate constant, and then go with the rate of consumption. So you're gonna do the this over change in time. Yeah. Because pretty much rate is the same, right? We figure out the rate. So rate is here. Yeah. You guys see that? It's from that equation where the rate is equal to negative changing x over change in time, except you use the coefficients 3, is equal to delta change in z over change in time. You already have z over t, which is that one, 2.4, and you want to find this. So you're gonna multiply by negative 3. Make sense? Yeah? Because this here is this. And they did tell you experiment 1. Because it's gonna be different per experiment that you will get a different answer. Yeah? Okay. You can double check if you're not sure. You can use your calculator to check it. See if that's what happened. Okay. 62. Again, has to do with this one, right? Single reactant and change. What happened, right? Lead to the tripling. Lead to the changing in 9 time. 3 and 9. What is the thing in there? Is the second order. 3 squared is 9, right? Second order. All right, let's do this one. Ooh, that's easy. Notice how like the first one is slow? Then you just write this. So you're gonna say K concentration of NO2 times NO2, or you can say NO2 squared. Sometimes they write it like this to show you that it's a bimodular or unimodular, stuff like that. Yeah. 64. B. Intermediate.
Oh, because NO2 is catalyst.
NO2 is catalase, yes. NO3 is the one that, this is catalase.
Oh. Wait, is one of them reacted the other catalyst?
You could be. You could be one of them is reacting and one come up. So not both actually, yeah. So one of them help with the catalyze this reaction. Yeah, I know it's kind of weird. No. As long if you have a slow step and it's part of it, you can write it like that. It's fine. That's why I said it's kind of weird. Like usually you don't have like catalyst and reactant as one thing. Yeah, that's a weird question. But anyway, either way, NO2 is not the intermediate, or neither this and NO. Yeah. All right, let's go through 65. I know it's a really weird question. Oh, elephant toothpaste. It's a little hard to do. You can, but it's a little hard to do because not just that, H2O2 has to be really powerful. H2O2, the normal, yeah, normal drugstore hydrogen peroxide is really weak. Is non-existent. Yeah, you need higher concentration for that to work. Yeah,
Wait, can you light it on fire?
you could kind of. Yeah, I mean you can probably reduce it, but yeah, and also they are very light sensitive, so they will decompose. Yeah. 66 and 67.
Hey. Yay.
Yay. Maybe next week.
Hey,
Oh, come on.
okay, question? That was an easy one. Now let's talk about the other one. The 12 question? Oh, 15 question. I forgot. How many questions was it? 15?
Yeah.
Yeah, 15 questions. Let me see. Where did I have my copy of? Right there.
Michelle, I got about a minute per question.
Yeah, go. A minute per
Michelle,
question.
roughly 1 minute to do each question.
How about I just go through everything? Number one, what do you guys get? D, and then number two.
D.
Yeah, is number two is not A. It should get B.
Yay!
Number three,
C.
C.
Yay!
Number four,
B.
Number five,
C.
number six.
D.
6A. Yeah.
Yay!
We'll go back to these if you guys have questions. 7, 8.
C. I see. I never got that 15 question.
8 is B.
Yay!
9.
D.
9 is D, you said? Yes. And then 10 is D also. 11 is C. 12. 13. 13 is B. 14
A.
and 15
D.
C. All right. So let's talk about things that we got wrong. Which one should we do? Can we do a 15? Which one would occur at the lower rate at the given temperature? Oh, you know why C? Because C has a huge activation energy, so it will occur at the lower rate.
So does A.
No, it's not. A activation energy is less
Oh.
because it don't go from reactant to the
Oh, no,
top.
look at it.
So it's 150, right?
I forgot that.
Yeah. So reactant to the top. Yeah? Glad we see this. Yeah? Yep. CYC for the 15? Alright. Wait. So I'm just going to go through. 11 is C, 12 is A, 13 is B, and 14 is A, and 15 is C. We good on the backside? Can I explain 11? Okay, following reaction. Oh, it's an elementary step. So you can just pick up these two coefficients. You can just pick up the stuff. So you can just say A, B equal to rate. So that's first order added together, second order. Okay? Yeah? All right, let's look at the first page really quick. 1 is D, 2 is B, 3 C, 4 is B, 5 is C, 6 is A, 7 D, 8 is B, 9 is D, and 10 is also D. Question about first page. I know I just spit out the answer with you guys, but question? 6. Let's see. Oh, first order, kinetic, constant temperature. Constant temperature, K is constant. First order half-life is 0.693 divided by K. Since K is constant, half-life is also constant. Make sense? All right, anyone from 1 to 10? 1? All right. Oh, it's a long one to read. All right, let's see. Magnesium react with hydrochloric to produce hydrogen. Experiment set it. Rate produce. Okay. Over 60 seconds, magnesium ribbon will cut to this and this volume of the hydrochloric solution. And the total mass of magnesium will held constant. Which condition is highest rate of production of this? Okay. So, yes. Mole concentration equal correct answer, right? So you have C and D to pick. Okay, you are picking D because smaller pieces. Because you don't have more or less mg. Because they said it here that total mass of magnesium is constant. So the mg doesn't change. What change is the pieces. Okay, so you have one piece of 1 centimeter square or the 2 pieces of 0.5, basically. You can imagine like that. So therefore it's D. Smaller surface. I mean bigger surface. More particles. Well, actually, it's not more particle. It's more exposed particle, you can say. But yeah, it's the same amount of particle. Okay? Because think about like, if I ask you to mix a pack of sugar or the block of sugar cube, assuming that they both have the same amount of sugar, the block is going to take longer to dissolve. The powder is better. The pack of sugar is better to dissolve. Same idea. Okay, 1 to 10. Any other question? Actually, I should say 2 to 10. No? We're gonna ace this? Yeah? Okay, again, you have to remember is this. Elementary step, we'll only look at the slow steps to look at the rate law. Okay?
How do they figure out the step is slow or fast?
They experimentally determine rate law and then they backward propose it. So those are all done experimentally. Okay? So, yeah. No. I mean, yes, kind of. Catalysts make things go faster, but it doesn't have influence on slow or fast. So meaning it's gonna speed up every single step. Make sense? So catalysts will speed up everything. So if you have an equation that goes forward and backward, it will speed up both directions, basically. So it doesn't control what the reaction is gonna happen, but it's control how it's gonna happen. It's gonna make it faster on either direction. They have to give it to you, otherwise you can't tell. Like remember there was one question, that trick question, that give you the rate, the equation, and ask you to find rate. You can't because I didn't tell you it was slow or fast. Okay, so it has to tell you. Otherwise, it would say like elementary step, finding the rate of this. Okay, so overall rate you cannot tell by just looking at one step. So pretty much most of them are looking at the tables like that and answering half-life, probably only first order. Looking at the line equation, not this. Well, actually I missed the line equation here, but yeah, line equation like this kind of thing, right? The ln or 1 over, right? So pretty much if you study that first sheet, one sheet that I gave you guys, the 0 first and second order, and also that writing how to write the rate equation, like what was this? I just write it. Like this. Also, right? So this is instantaneous rate equation. So like that, ln. Look at the rate order, integrate it, meaning look at which one is a straighter line, and write in an equation. That's it. You don't have a lot of equation. You only have that to do, and that's it. Okay? So should be okay, I'm hoping. Don't get confused with your thermodynamic kinetic stuff. Remember to pick up these individual important one. Okay? And for the free response, make sure write down everything. Like, remember, don't just tell me that temperature. Okay, well, temperature affect the reaction, yes, but how? Increase? Decrease? Which one are you talking about? Okay, I know some of you guys get lazy and you said TEMP. Okay, please write the whole thing, temperature TEMP. Or just write uppercase T. Okay, maybe it's better than saying TEMP. What else? Oh, and remember K has a unit for this chapter. Okay, rate constant K has a unit. And it's changing. Any question? All right, well, good.